Yeah, I was start in a second, just setting up some stuff. So I want to check the audio because we had to reinstall OBS. Had to reinstall OBS. Okay, I'll have to keep talking for a while to be able to test my audio. There's always a problem, isn't there? Okay, I should be able to. Still testing the audio. Yeah, the audio is fine. I'm using the correct microphone, that's a good sign. Yeah, I'll just rearrange the windows as well. We have a text to speech to text going. Speech to text. Do we have questions about this application? Yes, we're doing the scattering transform. Hey, can you provide a very quick overview of the whole conversation and the web application that we are trying to develop? Yeah, I'll read this quickly.
We are developing a web application to demonstrate how joint time frequency scattering can enhance seizure detection in EEG data. The discussion has focused on generating realistic EEG signals, applying a wavelet-based scattering transform, and visualizing the frequency content using FFT. The goal is to create an effective visualization for showcasing how advanced signal processing techniques can improve the detection of complex patterns, such as those found in seizure activity, ultimately helping in more accurate diagnosis and reducing patient risk.
Okay, that sounds good. I just need to reduce the audio for the robot. Wait a sec. Yeah, about -5 dB or so. We'll lock the volume to what it is. Okay, yeah, so making this web app. Yeah, there's some description at the bottom as well. Yeah, joint times frequency scattering. So we had some questions about it. Yeah, let's go over them and I'll just talk you through it.
Here are some questions you might consider. 1. Why does the scattering transform, red line, have more pronounced spikes compared to the raw EEG signal, blue line? Could these spikes indicate seizure-like activity, or might they also represent noise? 2. What do the major peaks in the
Yes, so yeah, the red line, the scattering transform, yeah, meant to indicate in a better way when you do have seizures. So when you have spiking in your EEG. But I'm not sure that's actually quite happening at the moment. What do you think? Yeah, we're, by the way, developing in a different way. We just so we have the code in scattering up. What was the last code? Yeah, this one. So we have the code. It's all JavaScript in HTML, no backend. So that's the good thing. Might make this a bit smaller. Yeah, and we're just editing in the text editor. Yeah, that's right. We're making 200 data points. Yeah, can you quickly explain what's up with the x-axis values? They look a bit weird. So if we select the whole code, pop the question in there. Yeah, those meant to be time a 1 to 200, and then we have frequencies. Yeah, more realistic levels such as actual timestamps in seconds. Yeah, sounds better. Yeah, that sounds good. So if it will modify the code, should modify the code. Sometimes it's really keen on coding. Other times it's being a bit lazy. I think it's an actual term. Okay, it's actually editing the code now. I think failed to edit. Okay, why? Okay, it's trying again. It's actually editing the code. Made 4 edits. Yeah, time in seconds. Let's see. Okay, this is better. So we have 200 lines of code, and we have frequency going from 0 to essentially 50 hertz. Don't need the trailing zeros. We do not need the trailing zeros. The it should be an easy fix. Yeah, we're actually not using Visual Studio Code today. I think that will be an improvement. Well, because we don't really need it, it's just heavy on the system. We're already streaming and everything. Remove the trailing zeros. Okay, let's do a code review. I think I can still copy. So I'm just using a notepad for modifying the code. What? No, that's not better, is it? Did you remove the trailing zeros? Or yeah, it sometimes will fail to comment. Failed to comment for. Yeah, it's still trying to do something. I guess it's like working with a human developer. To send them your code, then they don't respond for a week. Pattern mismatch. Yeah, it's like a weird. Don't quite understand how it works. If you need to select the whole thing first, or it's only 155 lines. I can fix bugs first, maybe. Okay, now it's actually editing the code. Maybe there was some sort of timeout after which it didn't recognize the code anymore. There's no point asking it questions about it. It will totally hallucinate. Currently 155, 157. Okay, found no bugs, but it did change the code. It's pretty funny. Okay. Now you're doing some rubbish. Okay, I think we have to revert it twice. Maybe once more. What's going on? The other thing is that we have a history in the notepad. Yes, we do. Okay, so we reverted back, and now this code, placing it into the canvas. But I'm pretty sure if I start asking questions just in the chat, it would not realize the code is there. So let's try a code review. Yeah, so currently every time there's obviously some randomness in the signal being generated, which is good. So this is simulating EEG brainwaves with spikes, with seizure spikes. Don't understand how it works. Seems like we need to fix bugs first. Still trying to get the hang of it. It's still yeah, this model GPT-4o with canvas is beta. Collaborate with a robot on writing code. Yes, we asked it not to use any external libraries for the data processing. So we're just using maths. Oops. I'm not sure. I'm not sure what's going on. Okay, reverting back. Might have to start a new chat. I have a feeling. Hey, can you open a new code canvas? Just pop in the HTML code that we currently have. Okay, why are you asking me silly questions? Yes, it's a HTML code that we currently have. What? Yeah, whatever. I don't know where you pulled that one out, but fine. Can just change it, assumingly. If we select HTTP explain. Yeah. This is just to make sure it actually has access to the code. Yeah, we're doing joint time frequency scattering. Yeah, hands-on demonstration sounds good. Now, if you can explain, could you explain the output as seen in the image attached? So doing this live streams, they meant to be interactive. I don't want to just talk to the robot. If there's any human who would like to talk, that would be awesome. Do let me know. You can just use the chat to begin with. Yeah, top chat, time domain, scattering transform, process the EG data after applying a wavelet scattering. So that wavelet scattering, I'm not sure if it's legit. No, I mean it's legit, but it's like simplified. I'm not sure currently how useful it is. It could potentially be made more useful. So currently the kinda seem to indicate where spiking in EEG is, but it's not ideal at the moment. Yeah, if we can make the scattering transform a bit better, that would be great. Now, in the frequency domain, should we also have two frequency charts? Well, sorry, no, one chart, but two traces. One for raw EEG signal in blue and the scattering transform FFT in red. Does that make any sense? Can you ask a lot of questions? Yeah, can you ask questions regards how to improve the code? Don't make any changes to the code yet. Yeah, it's a simplified version. Yeah, we could do more detailed wavelet transform. Currently we're using a fixed scale parameter. Yeah, we could make it adaptable, so that could be an input, a slider on the front page. So we can see by changing it, give it a default value, and by changing the slider, we shall see how the scale parameter affects the scattering transform. Yes, so regards the visualizing the frequency domain, adding two traces, one for the scattering transform. Yeah, I think we should have two traces in the frequency domain as well. Yeah, I'm not sure how comparing the two traces could improve the understanding of seizure detection. Well, it's just that if we have seizures, then the second trace should essentially look more like a seizure. Same as in the time domain. So we have the raw EEG, and then essentially the scattering transform makes the EEG look more like epileptic spiking. Is that the correct direction. Yeah, we can start there and see how we go.
I've added an input slider to adjust the scale parameter of the scattering transform. The slider dynamically updates both the time domain and frequency domain charts, allowing real-time visualization of the effects of changing the scale. Let me know if you need any further enhancements or adjustments.
Okay, a couple of things. Can in the frequency domain, the raw EEG could be in blue, so it matches the color pattern. Then the scale parameter at the moment doesn't seem to do much. I don't think. Looks like some sort of envelope, but it actually made more sense before. It's like losing the code or something. Okay, now it's actually
I've updated the frequency domain color for the raw EEG signal, FFT, to blue to maintain consistency with the time domain, and adjusted the scattering transform function to use a smoother envelope, making the scale parameter more impactful with an exponential decay effect. Let me know if this works better or if you need further adjustments.
Wait, so let me get it right. When we changing the scale, when we're changing the scale parameter, it's just refreshing the waveform. It's just generating a new waveform. I don't think we want that. We want to keep the waveform the same unless we refresh the page. So the waveform should be the same. Yeah, I'm not entirely sure what's going on. Can you explain the images? And what the difference does the scale parameter makes? So in low scale, the scattering transform retains most of the fine-grained details of the EEG data, preserving almost all high-frequency components. Okay, there's a problem that the frequency domain is not updating. When I change the scale parameter, only the time series is updating.
I've updated the script so that both the time domain and frequency domain visualizations are updated when the scale parameter changes. The FFT of the scattering transform is recalculated in real time to reflect the changes in the scale parameter. Let me know if this works as you intended or if further adjustments are needed.
And now I understand what is going on. However, something seemed to have changed in the raw EEG signal generation. Before we had more spike like periodic discharges. Can you explain first without updating the code? Yeah, we have combination of alpha, beta, and theta. Let's do a code review. And we have 2 seconds worth of data, but we probably... Yes, we have suggestions in the code. Yeah, we keep configuring it in the code, so we would like to actually the length of the raw EEG signal data to be configurable. That would be nice. Maybe 10,000 is a bit of a stretch.
I've made the length of the EEG data configurable by adding an input box for the user to specify the data length. This will allow you to generate different data sizes without altering the code. Let me know if there's anything else you'd like to adjust.
Yes, when the scale... So let me get it right. When the scale parameter is 0, the scattering transform is just essentially copying the raw EEG signal. When we increase the scattering transform, what exactly happens then? Hopefully this just goes in the chat. Can you give me a continuous text, one paragraph summary?
When the scale parameter is close to 0, the scattering transform essentially copies the raw EEG signal, as it uses only the current point or a very narrow neighborhood, which means almost no transformation occurs. However, as the scale parameter increases, the scattering transform becomes a wider smoothing operation, averaging each point with a broader set of neighboring points using exponential decay weighting. This process results in a smoother, less noisy signal that highlights broader trends and reduces fine-grained fluctuations, effectively emphasizing low-frequency components and reducing the visibility of sharp, transient features. This can be helpful in identifying seizure-like patterns by focusing on large-scale changes, though it might lose important high-frequency details.
Just in the chat, how is it then different from more basic filtering?
The scattering transform differs from more basic filtering methods in that it is not just a low-pass or high-pass filter designed to cut off specific frequency ranges. Instead, the scattering transform is a more sophisticated tool for capturing complex time-frequency characteristics. It uses overlapping windows and applies nonlinearities to extract meaningful features across different timescales. This helps in capturing both local and broader changes in the EEG data, making it useful for identifying non-stationary patterns like those found in seizure activities. Basic filters, on the other hand, typically focus only on isolating or suppressing certain frequency bands, without providing a multi-resolution view of the underlying signal. Essentially, scattering transforms allow for multi-scale analysis and emphasize hierarchical features that can reveal subtle and complex patterns, whereas basic filters do not offer this level of feature extraction. I've modified the code to update the chart data directly rather than destroying and recreating the charts. This should improve performance and reduce flickering when the charts are updated. Let me know if this works better or if you need further changes.
Okay, so it seemed to work pretty well. Can we actually explain? Can you actually explain the different FFT algorithms? That's in the chat. Yeah, we don't want to debounce. Hey, can you give me a one paragraph summary?
The naive FFT implementation currently in the code has a time complexity of O(n)2, which becomes inefficient for large datasets. To address this, there are several more efficient FFT algorithms available. The Cooley-Tukey algorithm is a popular choice that uses a divide and conquer approach to achieve a much faster O(n) log n complexity, making it ideal for large-scale applications like EEG analysis. Other algorithms, like radix2 or split radix, further optimize performance by processing data in different ways, especially when the data length is a power of 2. Additionally, algorithms like Bluestein's work well for arbitrary data lengths. These optimized FFT methods significantly reduce computation time compared to the naive approach, allowing for real-time analysis and better performance in biomedical applications.
Yeah, I'll just use the standard FFT for now. The scale parameter. Should this be 20? Should label go should label go first? Gets into requiring too many resources. 67. Can I close it for a sec? What's drawing my resources? So BS. It seems like I'm not using a GPU for streaming. Am I? Yeah, I might have to change the streaming settings. If you haven't done so already, go check out the website. This will be a new tool that will be adding. Ooh, my mouse is not visible. It says showing cursor. Okay, that's weird. I think we're using the wrong. Okay, we were using the wrong screen capture thingy. And now it's better because you can actually see the mouse. Yeah, can we actually update the description at the bottom of the page, including instructions how to use the tool, the general overview. And anything else you might think be useful for a description. See if it will just modify the code. And the other thing is, yeah, those things don't really look like spikes. We actually do have another tool. I think it doesn't have an image to it. Yeah, it's this one here. I have those regular seizures, periodic spikes. Can we actually describe how the generate EEG data works exactly? just give an explanation in terms of how to make the EEG with epileptic spikes to look more realistic. But don't change the code yet. Yeah, it's that bit there. The spikes. Yeah, let's read that one quickly.
In the current implementation, the EEG data generation uses a combination of different sine waves to simulate alpha, beta, and theta activity, mixed with random Gaussian noise and occasional spikes. The spikes are intended to mimic epileptic discharges, but they are generated randomly with a 5% chance per sample, math.random, rat 0.95, which makes them unpredictable and sometimes unrealistic. To make the epileptic spikes look more realistic, you could adjust several aspects. 1. Spike frequency and shape. Real epileptic spikes often occur in clusters or with a more structured periodicity rather than purely random instances. Instead of random spikes, you could introduce clusters of spikes occurring at somewhat regular intervals to better mimic seizure discharges. 2. Amplitude and duration. The spike amplitude currently varies between 0 and 4, which is somewhat simplistic. Realistic spikes could have different amplitudes depending on the severity of the event, and the duration could also vary, giving more diversity to the waveform. 3. Waveform shape. Rather than a simple sudden value increase, spikes in actual EEG data have a characteristic shape, like a sharp rise followed by a gradual decline. You could achieve this by combining several functions, e.g., a rapid sine or exponential decay function, to generate a more realistic spike profile. Before, background activity. Instead of adding spikes directly on top of a sine-based waveform, consider modulating the amplitude of the background rhythm to simulate how neural activity tends to change during an epileptic event. You could, for example, increase the amplitude of theta waves leading up to a spike, which would make the spikes appear more integrated into the overall signal. These changes would help make the generated EEG data more biologically plausible and help provide a better basis for observing how scattering transforms affect spike detection.
Yeah, it looks good at the moment. Yeah, probably didn't have to make this. We made the spikes much larger, but probably didn't have to. Yes, so essentially, yeah, if you can give an overview of this thing. I think there's a problem that yeah, so essentially we're labeling spikes. I think there might be an issue, there might be a bug in terms of that the frequency, the alpha, beta, and theta will depend. Are they currently depending on the EEG data length? Don't modify the code yet, just explain. The frequency is the variable I represent the sample index. Yeah, so there is this issue. Yeah, the sine wave should be explicitly defined. Okay, that sounds good. Can we explicitly define the different bands? Also, if we're already changing that, can we add more bands and the rest of the EEG bands? I would like to add them as well. And also, can we make sure that the baseline EEG is following 1 over F characteristic? Hey, Rohan. So we're doing, we actually could do a summary as well. So we have this joint time frequency scattering for enhancing seizure detection. I know it sounds too good to be true, but it's actually working. Where we have this scale parameter that you can change, and when increase, it will actually show you where spiking in EEG is more prominent. Will adjust your frequency domain as well. That's using wavelet, FFT and wavelet transform.
I've updated the EEG signal generation to explicitly define different frequency bands, delta, theta, alpha, beta, gamma, and added the characteristic 1F noise to make the baseline EEG more realistic. Let me know if you need further adjustments or explanations.
I'm not sure if it's what? Okay, that's just a bit weird. That's just a bit weird. Let's do a bug fixing for a sec. Suspect it will say it couldn't find anything. Doesn't look very realistic, does it?
I've reviewed the code and found and fixed several issues, including improving the efficiency of the FFT implementation by correcting how the real and imaginary parts are initialized and calculated. Additionally, I adjusted the frequency axis labeling to accurately reflect the sampling rate and data length. Let me know if there's anything else you'd like me to address.
Okay, we're now going places. Started getting errors. Yeah, I'm not sure about.
I've fixed the sampling rate is not defined error by moving the sampling rate variable outside the generate EEG data function, making it globally accessible. Let me know if there's anything else you'd like to adjust.
Can you explain the image? And just in the chat, without modifying the code, why does the raw EEG signal looks the way it does? Yeah, there's some sort of low frequency component that doesn't look very realistic. Can we actually make sure that the sine waves with the different frequencies, that the bands follow 1 over f characteristic in terms of its amplitude? Can you just explain in the chat how would you do that? You go and place it a bit while it's generating. You go check out the website. Everything we develop eventually available on the site. So to check it out, for example, we have this knowledge graph. Be actually useful if you're more visual. I'm more visual. Okay, it's actually seemed to know what it's doing. Hey, can you actually give us a quick summary of how would you modify the code? Because I'm not reading all that, but it seemed to know to adjust the, essentially give weights. Giving weights. Okay, let's read that, that's important.
To modify the code so that the sine waves follow a 1f characteristic in terms of their amplitude, you would 1. Update the amplitudes of each frequency component in the generate EEG data function. Instead of fixed values 0.8, 0.3, 0.5, etc., use a calculation that makes the amplitude inversely proportional to the frequency. 2. Specifically, for each frequency component, delta, theta, alpha, beta, gamma, set the amplitude to one source frequencies, band. For instance, const delta equals 1 of frequencies dot delta to math sin, const theta equals 1 frequencies theta, math sin. 3. This modification ensures that lower frequencies have larger amplitudes and higher frequencies have smaller amplitudes, following the star F rule. This adjustment would make the generated EEG data more accurately reflect the distribution of power found in real EEG signals, where lower frequencies tend to dominate in terms of amplitude.
Can you modify the code accordingly? Because currently it doesn't look very realistic, the raw EEG signal.
I've updated the code to adjust the amplitude of each frequency band according to the Schwarzschild 1 of F characteristic, ensuring lower frequencies have greater amplitudes compared to higher frequencies. Let me know if you need further modifications or explanations.
So we adjusted the amplitude of each frequency band according to the 1 over F. Yeah, but that let's do a code review on that bit. Does it work like that when you select? Consider improving the efficiency of the noise generation and reducing the dependency on the loop iteration. Yeah, we don't need the noise, do we? Oops. Yeah, the noise bit. Okay, let's try that.
I've modified the EEG data generation function to improve the efficiency of noise generation by pre-computing noise values, which should reduce dependency on loop iteration and improve overall performance. Let me know if you need further adjustments or explanations.
It's like it feels like we had it better before. So can you explain? So we providing weights to. So we are providing weights to the different frequency bands. Is that correct? To try for it to look like 1 over f, which gives a more realistic baseline EEG. On top of it, we have spikes. Do we still need the noise or not? It feels like we should either have the 1 over f noise, which will mimic baseline EEG, or the combination of sine waves. I'm thinking just trying the noise alone and the spikes on top of it. What do you think? I don't know if it will start modifying the code or not. Let's see what it does.
Your thinking is definitely on point. Since the idea is to create a realistic baseline EEG, you could indeed experiment with using just the 1F noise to generate the baseline activity and then add spikes for seizure-like behavior. Option 1, just noise and spikes. If you use only 1F noise, the 1F noise alone can effectively simulate the general background activity seen in EEG, where lower frequencies dominate. By adding seizure-like spikes on top of this noise, you would keep the EEG simpler, but still realistic, focusing more directly on highlighting seizure events. This approach can reduce complexity, making it easier to visually interpret and identify the spikes amidst the background activity. Option 2, combination of sine waves and spikes. If you use sine waves plus spikes, including sine waves for specific frequency bands, like delta, theta, alpha, etc., creates more structured rhythms within the EEG. This adds complexity and richness to the background, which is more typical of real-world EEG, but it may make identifying spikes less straightforward because the structured oscillations can sometimes mask them. Recommendation: if your goal is to keep the signal clean and emphasize seizure detection, starting with a F noise only could be a good idea. This way, the background EEG reflects typical brain activity without predefined oscillations, and you can clearly see the effect of added spikes. Would you like me to modify the code to remove the sine waves and use only the noise plus spikes? This will help keep the focus on making the epileptic spikes more distinct against a naturalistic background.
Okay, so we removed the sinusoids. It looks good in terms of baseline EEG. Well, we don't know because the spikes are too large at the moment. What the signal to noise ratio? What's the spike to noise ratio should we use? Well, it should be called the spike to baseline EEG. Should we have another input slider for setting the no, we should not. Now this lowest and reduce the spike amplitude 2 or 3 close to the noise level. Okay, that sounds good. Yeah, if we can reduce the spike amplitude to 2 or 3. Can't actually find it in the code, but we have a developer, so let's okay, actually edit it to 3. Yeah, it could be 2 really. Yeah, that's the thing about it. It's not taking, when you edit, it doesn't take stuff into effect. Yeah, the spikes are still way too large. That's a bit weird. The scale parameter. Yeah, I'm pretty sure I changed it to 10 before it didn't take effect. The spikes still seem too large. Any suggestions as to how we can change the code? Reduce the spike probability, 2% chance. Lower the spike amplitude. Can we increase the noise instead and make the spikes more realistic? So if it will just adjust the code.
I've increased the noise level by modifying the noise generation factor and reduced the spike amplitude further to make the spikes more realistic compared to the noise. Let me know if this achieves the desired effect or if you'd like more adjustments.
Okay, this does look better. Can you explain the image? Ask questions. Don't modify the code yet. I think we did pretty well.
In the updated image, we see the raw EEG signal in blue and the scattering transform in red. Here are some observations and questions. Observations. 1. The raw EEG signal has both noise and occasional spikes, but the spikes are much smaller and less dominant now compared to before. The overall appearance of the signal is more subtle, reflecting a more realistic baseline activity. 2. The scattering transform appears smoother, emphasizing broader features while reducing the influence of high-frequency noise. This effect is more evident with higher scale parameter values, where sharp peaks are spread out and more gradual. 3. In the frequency domain, FFT chart, we notice both the blue and red traces have energy concentrated at lower frequencies, which is typical for 1F noise. Questions to explore. 1. Are the spikes clearly visible? Do the spikes appear sufficiently distinct from the noise to be considered seizure-like? Or are they blending in too much now? 2. Scale parameter adjustment. How does changing the scale parameter impact the detection of the spikes? Does increasing it make the spikes harder to identify, or does it help differentiate the spikes from the background noise? Frequency domain clarity. When looking at the FFT, is there enough distinction between the raw EEG and the scattering transform signals to help with analysis? Or do they look too similar now that the spikes have a lower amplitude? 4. Realism of baseline. Does the baseline EEG signal, now dominated by noise, provide a realistic background that represents typical non-epileptic activity? If not, should we reintroduce some structured rhythms like alpha or theta waves? 5. Spike characteristics. Should we try to make the spikes even more natural by giving them a distinct shape, e.g., faster rise and slower fall? This could make the seizure-like events stand out more without needing high amplitude. These questions can guide further improvements in making the simulated EEG data useful for exploring seizure detection and understanding the effects of signal processing techniques. Let me know if you'd like to tweak the parameters or explore any of these aspects further.
All right, so yeah, the last suggestion, number 5, the spike characteristic sounds good. So we can reduce the amplitude, probably half it. And yes, make the spikes look more realistic. I do maintain the clustering of spikes that is there already. So keep that going. So it looks good overall, but the shape of the spikes doesn't look very realistic. And yeah, the amplitude can be reduced a bit. So yeah, while it's generating, go check out the website. Everything we do is eventually on the front page there. We're doing a training model as well, so go check it out. Check out the results of the model training. There's a lot of interesting tools that sure you'll find something that interests you.
I've modified the spike generation to have a more realistic shape with a fast rise and slow fall by introducing a new generate spike function. This creates spikes that are less abrupt and have a more natural amplitude decay. Let me know if this looks good or if further tweaks are needed.
Okay, we're getting an error. Was we'll be able to solve it quickly. Line 59. Yep. Well, could have solved it ourselves. Okay, now, well, I can't see the spikes myself, which is a bit of a problem. Okay, can we try keeping the new spike shape, but increase the amplitude of the spikes a bit? Just to have this multiplier there. I was looking at the wrong place in the code. It's good that we have a professional developer. Okay, this okay. I'm not sure if it's much better. Okay, let's do a quick code review and yeah, I'll just deploy it on the website. Forgot the name. Time frequency. Considers generated a noise cache using a more sophisticated random distribution such as Gaussian distribution to better. Okay, why? I don't know why. The spike generation is currently random and may not always align with the realistic seizure when consider clustering. Yeah, clustering, that's what we were asking for. we like clustering because that looks like would look more like an epileptic seizure. Should look a bit more realistic.
I've modified the spike generation to use clustered bursts rather than isolated spikes, making it more representative of seizure-like activity. Let me know if this achieves the desired effect or if further tweaks are needed.
Yeah, it does look good. The loop structure could be optimized. It's not a large data set, so it should be fine. Yeah, we don't want to debounce the slider yet. Can we update, rewrite, and extend the explanation of the web application at the bottom of the page? Yeah, we could also make sure that there is at least one spike cluster. Yes, if you have any ideas for new tools or updates and modifications to current tools, do let me know. We have how to use a visual presentation application overview.
I've extended the explanation at the bottom of the page to provide a more detailed overview of the tool, its uses, and how to interact with the various parameters. This expanded description helps users understand both the purpose and the operation of the tool more comprehensively. Let me know if there's anything else you'd like to adjust. I've added comments to suggest improvements for noise generation, FFT efficiency, spike clustering, wavelet scattering transform optimization, and chart update performance. Let me know if you need further modifications or detailed explanations on any of these points. I've updated the spike clustering logic to use a probabilistic model that adjusts the duration and frequency of spike clusters dynamically. This should create more realistic bursts of seizure-like activity. Let me know if you need further refinements. The suggestion for optimizing the loop structure is focused on improving the computational efficiency of the wavelet scattering transform function. Currently, this function uses a nested loop to iterate through each data point and perform calculations over a window defined by the scale parameter. This approach has a computational complexity of O(n) to 2 scale, which can be inefficient for larger data sets. Here's a detailed explanation of potential improvements. Number 1. Windowing or convolution approach. In the current code, the inner loop for calculating the value of each transform data point looks at neighboring points based on the scale parameter. Instead of explicitly iterating over this range for each data point, a more efficient approach would be to use convolution operations. Convolution libraries, or tools like Fast Fourier Transform, FFT. SOT-based convolution can significantly reduce the time complexity. Convolution is essentially a sliding window computation that can be optimized through specialized algorithms to compute the output faster. Using existing libraries such as TensorFlow.js, Sci.js, or other optimized JavaScript packages for convolution could help reduce computational load. If the kernel, which determines how neighboring values are weighted, remains fixed or is symmetrical, FFT-based convolution could be used to take advantage of the properties of the Fourier transform, which can reduce the time complexity from O(n) const scale, ta, to approximately O(n) log n. 2. Avoiding redundant computations. Currently, the inner loop recomputes the envelope weights, math.exp math.j/scale, for every data point. This is redundant if the weights only depend on the window offset, j, and the scale. Pre-compute weights. Pre-calculate the weights for the envelope once and store them in an array. This way, you can reuse the same weights for every data point. This optimization avoids repeated calls to the exponential function, which can be computationally expensive. 3. Sliding window calculation. Instead of recalculating the entire sum for each position in the data array, a sliding window approach could be used. Sliding window optimization? When moving from one point to the next in the data array, rather than recomputing the entire sum for the new window, you can adjust the previous sum by subtracting the value that left the window and adding the new value that entered. This can reduce the time complexity from O(n) na scale stara to approximately O(n) ra, making the computation linear in terms of the length of the data. Implementing any of these optimizations could improve the overall performance, especially when dealing with large EEG datasets, which tend to be computationally intensive. Would you like me to proceed with implementing one of these improvements?
website. Go check it out. Let me know if there's any questions about it. What did I do wrong? Probably quite a few things. There's a description at the bottom of the page.